Yeah, one kid I was hanging out with last night is boycotting Meta, I guess. He's like, he deleted all of his Meta accounts, all of his, anything associated with Meta. I was like, oh, why?
I mean,
doesn't like Meta. I'm like, fair enough, honestly. Like, I can't judge.
Yeah, no, it's good. Good luck trying to get away from them.
Yeah, it's not happening for sure.
Yeah. All right, what is, oh, it's time. Yes, hey, howdy everyone. Sorry, I'm on some weird time zone. It's called Fuzzy Town. Fuzzy Town time zone. And it's just the way it is. Let's do a nice bell meditation. So, I'm gonna wait till everybody's with me. Wait till Mr. Czar's done, whatever the tech is going on over there. You all good? All right. Look who's back. Look who's back.
Oh, Mom.
We missed you guys.
I was gone for a while.
You were gone for a while, so was Mr. Uthman. All right, sit up straight, even if you're Czar. Sit up straight.
Facial posture.
Yeah, let's practice posture. Just take a second to tune in to whatever sensations you notice as soon as you close your eyes. What do you observe about where you're at right now? No wrong answers. I'm gonna ring this bell. We're gonna let this bell wash over us. So imagine you're just diving into some cool water. That cool water is this tone. Re-enter the world. I could barely even summon the words to like lead us through that low energy meditation. It's like I'm letting the bell do most of the work and I can barely even get the words out. So Wednesday we've got skill checks. All right, doing skill checks on Wednesday. There are we've got some web works that allow you to practice on those. Is there anything you want to talk about? Evan and I were talking about one of the Lagrange ones earlier today. And you either know if you want to talk about this because you've done those problems, or you don't want to talk about them, probably because you have not done those problems. Yeah. All right. So I'm going to move on though a little bit today. Gosh, did I even hit record? Would you mind just? I'm sorry. Would you just?
Yep.
Thank you, sir. That's how out of it I am. Let's look at a new kind of problem. So we've got what? 5 weeks?
Yeah.
Including this week. Insane. So, oh hi. The rest of this course is on integration. That's the rest of everything we're doing. So derivatives, they're in the background in that you have to be able to take antiderivatives to do integration. But I want to look at a new problem today. So I've got some weird surface. And this surface lives above a rectangle in the plane. So it's yeah, that's pretty good. Cool. So we're we're going to set up a very simple problem, then we're going to complicate this problem every time we meet. The first problem is I've got this surface z equals f of xy, and I want to find the volume that is underneath this surface that's formed above the xy plane. So can you imagine you've got this weird tower here, like this, extending those down. So I've got this thing like this, and it's a solid that looks like this. And then, so that's like kind of the isometric version there. I want to find the volume of this thing. Integration is going to be our answer. In the same way that when we want to find the area underneath a curve, we use integration. We're going to do the same thing here. We just got more variables floating around. Real quick reminder on how this worked. We literally did this like day 2 of class. I think day 1 was everything about derivatives. Day 2 was everything about integrals. Remember how this worked. I had this closed interval and y equals f of x. I cut this into n pieces. They didn't have to be all the same. So I said x naught is the left end point, and then I pick an x1 to the right, and x2 to the right of that, and then all the way down to x sub n. Got a little excited there. And then x sub n was my right endpoint b. So this was called a partition. So we partition the closed interval a to b into n parts. Then I choose a representative in each of the n little subintervals. So I choose this x sub I star that represents the whole little subinterval in there. So this is going to be in x sub I minus 1 comma x sub I. So for example, x sub 1 star, just so this doesn't freak you out, is in x sub 0 comma x sub 1. So it lives in there. That's where x1 star lives, between these 2 points. x2 star lives between these 2. I have used that as the representative for the whole interval, and I'm going to figure out what is the height of the function there. So I go up, grab the height, and I use that as the height of the rectangle I'm going to put there. So this is the height of the rectangle, the ith rectangle. And then here I had delta x sub I, and that's just the width of each of these intervals. So it's x sub I minus x sub I minus 1. That's how wide your rectangle is. And we summed those things up from 1 to n. And then we let n go to infinity. And this turned into the integral from a to b, f of x dx. So I hope that none of that's shocking. You might not be able to like get up and do a little lecture on it or anything, but this all sound familiar. Cool. Same thing here. But instead, so today we're going to start off pretty chill. So here's my x-axis, here's my y-axis. This is going to be b, this is going to be a. So I've got this interval from a to b on the x-axis. On the y-axis, I'm going to start at c and run to d. So this piece we have in the xy plane, looking straight down, looks like this. A to b here, c to d here, and I've just got the nice little rectangular base. So that's my base down here. That's this thing down here. So what we're going to do is cut it into little pieces, make each piece represent the whole thing somehow. But we've got double cuts to make here. So what we're going to do is we're going to partition the interval a to b into m pieces. So that's an m there. Because I don't necessarily want to cut these under the same. I don't want to cut 5 here and 5 here. I want to be able to do 10 here and 1,000 here. I want to be able to have different numbers of cuts on each axis. So that's going to look like this. x1 plus something like that. x sub m is my right end piece. Okay, so I'm just going, here's x1, here's x2, blah, blah, blah. And then x sub m is that very last one. I'm going to cut the y-axis up. So I'm going to partition, that's a great word, partition, C to D into n pieces. Notice I'm not saying they're all the same width either. Doesn't matter. This is going to look a lot like what I did there, except we're going to have y's. So the C is y sub 0 less than y1. So like this might be y1 here. This is y0, y2. And just kind of keep on going up. 2 dot 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 less than y sub n. And that's my top end point. So here I'm going to do n pieces, here I'm going to do m pieces. Each of these cuts produces up here either a vertical cut where I've cut the x's, or a horizontal cut where I chose the y's, but it ends up cutting that little rectangle into how many pieces? How many pieces are in here? What's that? M times n, is that what you were saying? Yeah. Okay, I thought, okay. M times n. So we're going to cut this into m times n pieces. What we're going to do then is pick a point out of each one of these as a representative, just like we did before. So now, choose in each of the little sub-rectangles. So actually, let's write up what I just said. This board's working good today. That's nice. So this partitions the rectangle base, and the rectangle base looked like this. It's A comma B crossed with C comma D. Does this notation look confusing or make sense? Do you see where I'm getting that from? That X, this represents the Cartesian product, but it's just literally this space right here. This is AB crossed with CD. It's that whole collection of all the points in there. This means the X coordinate comes from here. So this is all X and Y's. So the X comes from here and the Y comes from here. Just all those points, in case that notation looks weird. So this partitions the rectangle base into m times n subrectangles. For each rectangle, choose a representative. So I'm going to choose an x sub I star, comma y sub j star. I'm going to use different indices there because those are going to move independent of each other. In each rectangle. Oh wait, I already said that. For each rectangle, choose inside the rectangle. I'm saying the word. This is terrible English here. The word rectangle seems to appear way too many times, and so does that Euler. Inside the rectangle. So this is going to be I equals 1 to m, and j equals 1 to n. If you were doing for loops, you'd have a for loop for that and a for loop for that. We're just choosing all those guys in there. These will represent their entire rectangle. So these points represent their rectangle. And we're going to use them in the function f of xy to get the height. So f of x sub I star, y sub j star, is the height of the I comma j. What do we call these things? Rectangular prisms? Rectangular prism. So the height here is going to be f of x sub I star y sub j star. That's how high that little guy is. And the base is delta y sub I delta x sub I. Now I'm starting to worry. Am I communicating what I'm trying to communicate here? Okay, good, because it's like I'm so fuzzy today that I almost feel half in the world and half out of the world. It's very odd. I hope it's not some weird sickness coming down again. So we've got this shape that we originally had, but after we get done with this, we're going to have this weird approximation of it, right? So it's going to look like a Minecraft surface more than anything. Do you know what I'm saying? So I'm taking this weird round thing, but I'm replacing each piece of it with one of those little towers like that. So it's going to look like, I could draw it, but it would take forever. It doesn't sound fun to watch or to do. Do you all know what I'm saying? Minecraft approximation? Okay. I feel like some old guy who learned about Minecraft and now I use that to relate to people younger than myself. And I guess I do. But I've played a lot of Minecraft. Like I feel legit pulling it up. Okay, so the sum of the volumes of these rectangular prisms, of these m by n, m times n rectangular prisms. Yeah, exactly. Is approximately the volume we seek. Let's write that all up. What was that going to look? Oh, sorry. So first off, I've got a sum I equals 1 to m, and then I've got a sum j equals 1 to n. This is going to be the height of that particular prism. And then here I'm going to put delta x. I'm going to write this a couple different ways. Delta x sub I, delta y sub I. So let's just write that. Y sub j, excuse me. Y sub j. So this is your base area. And I'm going to change that, just making that note, and then this is the height.
Dr.
Yes?
So are the sums that you drew, are they like being multiplied to like show n times n? Or is that just?
Yeah, so this one here, this is going to run over all the different x values. So this is kind of like, first, so how would this sum work? Is that, I think that's kind of what you're asking, right? So the way this sum would work is, I'm going to let I run from 1 to m. I'm going to let j run from 1 to n every time I pick a new I value. So for example, Alex, we're going to have I equals 1. And then that's going to be, we're going to have this whole sum here like this. That is just f of x sub 1 star, y sub j star, delta x sub 1, delta y sub j. So when I equals 1, I got this whole sum here. I'm going to crank that out. And then I'm going to let I equal 2. And that's going to produce a different sum with x sub 2. And then I'm going to add these all up.
And those are just n subs?
Yes, sir.
Okay.
Yeah.
And then they're being multiplied with the same thing, but with for n for the y values?
Yes. Yeah. Does this sum, let's make sure we understand what I've just written. Because if we don't understand this, then I don't want to take a limit on it. Christian, yes, sir.
This is kind of a simple question, but I'm still like a little bit caught up on like that sum thing.
Yeah.
So you're like summing the values for x that would be like your I to m, right? And then you're summing the values of y, which is like your j to n, and then you multiply those together.
Yes.
Okay.
So essentially, I'm kind of thinking of every combo of I and j. And adding all those results together. Let's look at a very specific one. So what if I had some I equals 1 to 2, some j equals 1 to 3, and then this stuff here. X of I star, y sub j star. I'm glad we're talking about this. Delta x of I, delta y sub j. So this is going to be 6 different things. There's 6 different pieces to this sum. So first off, when I equals 1, I've got f of x sub 1 star, y sub. So I'm going to let I equal 1, and then I'm going to let j run. So I've got y1, delta x sub 1, delta y sub 1. So I'm still going to keep x, this I index equal to 1. So then I've got f of x 1 star, y sub 2 star, delta x sub 1, delta y sub 2. And then I got one more. I've got j equals 3. So f of x sub 1 star, y sub 3 star, delta x sub 1, delta y sub 3. And then I do that again. Is that making sense?
Yeah,
Yeah, so then plus, then I'm going to have the same thing here, but I'm going to have x2 star and delta x2. So here I'll have x2 star, delta x2, x2 star, x2.
So like if you were looking at it like down at like that grid and like the XY trace, you're just like moving. Like,
Yeah,
like,
exactly.
like-
Yeah, 100%. Yeah, so we're just going through this grid and we're saying, here's when I equals 1, that plus that plus that, then plus I equals 2, and adding up literally all those values. Yes.
That makes sense.
Okay, cool. Any other questions? Anything else I can do to help clarify that?
Is the sum
Yes, sir.
that you just wrote, is it just doing the, because you kept x1 the entire time, so are you only like doing the j?
Yeah, so let me finish writing this up so that it's a little clearer here. I think this is what you're asking. So plus, and then, so then this next one. So here I let x, I'm just dealing with all the x1 stuff and letting y vary. Here I'm doing x2 stuff.
Okay, yeah.
So maybe if I write this out, it actually helps.
So like every time you go, so on that, if you go to that picture,
Yes, sir.
that, so you, okay, where your left finger is, that's
Yeah.
like x1.
Yep.
And then when you go up, that's like that's x1, y2.
Yeah.
Okay.
Yeah.
Okay, I got that.
Yeah, so that's 1, 1, 1, 2. Yep, exactly.
Okay.
Yeah.
I got that.
Cool. Awesome. And let me just finish writing this up so that it's actually, oh wait, that's delta x sub 2, y sub 3, delta x sub 2, y sub 1.
Yeah.
Cool. Okay. Awesome. Cool. Good. Thanks for asking questions. It's super important. Because what we've got now is something that looks like a Riemann sum, except it's a fancy Riemann sum with double summations in it. But what we're going to do is we're going to assume a couple things. First off, we're going to assume that f is continuous. So there's no jumps, there's no asymptotes, it doesn't fly off to infinity or do anything funky. And we're going to let m and n go to infinity. The number of cuts go to infinity. So we're going to let m go to infinity and n go to infinity. What do you think this turns into? This is the perfect volume. Yeah, it's the perfect volume. What do you think symbol-wise? What do sums do when you take that limit in the Riemann sum? Double integral. So each of those sums goes into an integral. This outer one, this was for x. This I here, this was for the x, and the x ran between a and b. So I'm actually gonna put that on the inside, and then the b goes, or excuse me, the y went from c to d. This just turns into the function that we had, and then this is dx, dy. And I want to talk about this. There's a lot of little subtleties that we want to talk about here. So I got C and D. So notice, first off, that this x is the interior differential, and it goes with the interior integral. So this dx is referring to this range right here. It tells me that the x goes from a to b. So first, do the x integral. Then you work that through, and then it's like two nested integrals. Then do the y integral. And this is what we're going to spend a lot of time messing with today.
Dr. T?
Yes, sir.
Does it matter which angle you do first?
No, let me show. Yeah, that's a good question, Evan. So we could. It doesn't matter from a thing called Fubini's theorem that we can, but you have to be careful. So I could also write this in this way. I could put the dy dx and do the y first, and then the x. I just got to make sure that this is the y range here, so that this would be c to d, and this would be a to b. But in general, it's probably better to work inside out just as a common practice. But you could rewrite this in this form, do the y stuff first, as long as you make sure that you get the y running from c to d. Is that what you're asking, or maybe not?
Yeah, I just got confused because we equated m pieces to a and b, and n pieces to c and d. So I was just flipping it around in my mind.
Gotcha. Yeah, and then those just went, the m and the n just went away as we took the limit, as the m and n went to infinity. Then it just becomes this. You don't have to worry about the m and n. Does that sound okay?
So if you're solving like the y integral with respect to y, you could do that one before the x and or the other way around.
Yeah.
Right.
Exactly.
And the notation just has to be so that you're. All right, I see.
I think let's do some solid computations. It's going to feel a lot better once we actually do. Yeah. Yes,
Do
sir?
the double integration when we have just the double sum, right?
Yes, yes. Let me actually show you a slightly different way to write this. Notice how I could have written it like this, and I could have written it like this. We could also write the whole thing like this. So the general process is double integral over that rectangle. I'm just going to put R here, where this is the rectangle, A comma B cross C comma D, f of x, y, and then here I could put dA for area. And notice that here, x times y is the area, y times x is the area. But one of the fun things we're going to do is use different things for area after we get a little better at this. Like when we go to polar coordinates, we might have cool ways to find the area of our area elements. So this can be written like this or like this, and that's all part of something that you don't need to know the name of in this class, really, but it is called Fubini's theorem. That says that if this process of cutting up that rectangle and doing those weighted sums like we did, that's represented by this, and this is a specific instance, and so is this. Let's get a new color. Let's do some actual calculus cranking and have some fun here.
Here's your rag right there.
What's up? Oh yeah, rag. Yeah. That rag's probably why I've been getting sick. I mean, it looks loaded with goodness, doesn't it? Looks like it needs a wash. I think it needs a wash. Yeah, I don't think my wife wants me to put that in our washing machine, no. So
You should have bought me one at Ace.
I should have a big bag of rags. Yeah. They're always willing to help you. There's always someone ready to help you at Ace. Oh yeah. So let's do this. I'm going to write this in a fancy way here. And let's say we have x plus 2y, and then here we're going to have dA. So we want to find this integral where r is this rectangle. It starts at -1, runs to 2 on the x-axis, and then 1, 2, 3, and then it goes between 1 and 4 on this axis. So in other words, on the y-axis. So notice how it runs from -1 to 2 on the x-axis, that's its width, and then 1 to 3 is its y range. So here r equals -1, 2 cross 1, comma 4. So it's a little bit of a new type of notation, just thinking a little bit differently. But we want to do this integral, and we can do it multiple ways. We could do the x first or the y first, and so really it's like up to you. Yeah, exactly, yeah. You just call it. So you want to do x first, it sounds like. Zara says we're doing x first, and that's cool. So let's rewrite this. Let's do the x first version, which means I'm going to copy this thing down, and I'm going to put dx on the inside, and that's going to be paired with this integral. And x runs from -1 to 2. And then I do the dy, which ran from 1 to 4. So let's do this one together. Because we have to do partial integration, partial antiderivatives. So now let's take this thing here, and we're going to do this, and we're going to integrate it with respect to x. So notice that y is a constant, x is the variable. Where does x go when I integrate it with respect to x?
X squared over 2.
Yep, x squared over 2, 1/2 x squared. What about 2y when I integrate with respect to x?
2xy.
2xy, it's just a constant, it's like 7, right? 7 would go to 7x, so plus 2yx. And that's going to evaluate. Now, I highly recommend putting here the variable. That means x runs from -1 to x equals 2. And let's still copy down this outside integral. So we still have this external integral for y. Notice how I'm using notation to keep my brain straight. So we're only going to replace x when we plug those n values in. So this is integral 1 to 4. Plug in the x, and you get 1/2 times 2 squared plus 2y times 2. So I'm putting the 2 in for the x. Minus, put in the -1. I'm really right, and put in parentheses here too. You'll just be a happier soul if you do that. Plus 2y times -1 dy. Let me stop and let me know if that all looks cool. You see where I'm getting it. And if you want to just start cranking ahead, you can. But I'm going to spend some time simplifying this. So let's see. So that's 2 minus 1/2. That's 3/2. And then we've got 4y plus 2y. So check me out on this and see if we all agree. And make sure you can get there. Like it's, you can look up there and go, oh yeah, it's totally what I would have done. So, but just make sure that it is what you do. So I'm going to thank you. That is a 6, not a B. And if you want to take it home, go for it. Might actually push this to an interesting place today. Once you get there, you just go ahead now, just treat that like a Calc 1 problem. Antiderivative of those, 3/2 goes to 3/2 y, 6y goes to 3y squared, and plug in those things and you're good to go. Yeah? Okay, cool, awesome, nice. So what I would like to do is let's try this in the other order, just for practice. So we did this integral. Let's do this integral and make sure we end up with the same thing. So -1 to 2 is the last thing you do. X plus 2y, maybe 1 to 4. Let's just check it out. dy dx. Try that, just to make sure.
Where's the constant come in? Let's see.
When you're doing definite integrals, you just kind of leave it off because it would cancel anyway. Does that make sense? Yeah. Did you get COVID? Is that what
I got a
happened?
cold.
What's that?
Cold.
Cold?
Yeah.
That's a bad cold.
Is it? I got better on Sunday. I just had a little bit of a cough.
Oh, okay.
But yesterday.
But you're feeling lots better and
Yeah.
awesome.
I've been feeling better since yesterday. but-
Cool. This direction actually seems a little nicer, doesn't it? Yeah, it's, you know, shockingly better. That's crazy. I'm almost not believing this is the same answer. Looking like the same answer. 6. Yep. Cool. Just be able to do it both ways, but you can see one way is kind of a little nicer aesthetically, maybe just like emotionally. If for some reason this just feels a little slicker. So make sure you can get 49.5, or could get 49.5 if you checked your actual fine lines. How do we feel on this? Yeah? How do you think we would do this in general if we had 3 variables? So what if I had integrate f of x, y, z equals x times y times z. Why not? Over the 3D rectangle, let's call it C, is a cube kind of thing, that is 0 to 1, cross 0 to 2, cross -1 to 1. How do you think we do this?
Let's do it integral with respect to z.
Triple integral? Yeah. Just take a minute, set it up, and let's check. That's right. I'm just writing it a fancy way than the way you might have ended up writing it. So you can pick any of the, I guess there's 6 different orders here you could have, actually. Because you've got 3 ways you can choose the first one. Once you choose that, there's 2 choices left for the other 2, and then once you pick the first 2, the final one's chosen. So that's 6 different differential combinations here. But as long as things are synced up, with the dx being the x range there, so 0 to 1, my y runs from 0 to 2, and my z runs from -1 to 1. Yes, ma'am.
Location-wise, for the dB, can it still be dA, or does that have to change?
Well, we would probably, since this is actually a volume,
Oh, okay.
so the thing, so like this one
Okay.
here, yeah, do you see what I'm saying, Camila? Yeah, we're gonna split that into little cubies. Yeah, it could be A, but
Yeah.
it's a little more suggestive with the B, yes.
So like, what does this do? Like, are we like finding the volume of like 4-dimensional shadow? on, like,
Yes.
a-
Yeah,
Okay.
that's about right, yeah, the volume of 4-dimensional thing, yes. Yeah. Yeah, I mean, the way to think about this really is, you could think of this as maybe like a temperature measurement inside here. And you're figuring out the average temperature over this weird cube that where the temperature can vary depending on the coordinates. So that would be one way to maybe think of this without having to go crazy into the 4th dimension. But I like the 4th dimension. Can you do that integral for me, please? Did something wrong.
So I don't believe this.
Come take a look.
I don't think I'm supposed to be 0.
What's going wrong?
So that, I don't think it was supposed to be 0 to bring it back.
I don't think so either, but yeah, no, maybe. Hell, maybe. Yeah, let's take a look. I honestly, I don't know, Czar.
I
Didn't get 0? Okay, well, let's see how you got. So let's see. So first you did your x.
I didn't show
I
myself.
like it. No, that looks good. And then you went 0 to 1. That looks pretty solid. And then you went to your y. Your y went to 2. So let's see. See, how do you look at? Oh, I see. So you can see. Well, shit.
I also
I
got
got
0
as well.
I think it's 0.
I think you just happened to do that.
Let's check it out. Yeah, good work, Czar. Yes, sir.
Yeah, but look at the lemma, like, that is definitely 0.
Yeah, you
So, let's see, so
Yeah.
right, so the x is the inside.
-1.
This is 0 to 1. And then start with that. So start with the x, integrate with respect to x, so the y and the z are constant. So
What about the
and
one
then
with
do the
the-
y
with
and
the
the first
hand
one.
roll?
Yeah.
Second one.
Do you have a question, Christian, or you just?
Oh,
checking out?
Did you see the base?
I haven't looked at it yet.
That was pretty fast, Czar. That was pretty fast, man.
Well, that's what I thought I did it wrong.
You got it right. I think.
And then especially coming out of 0.
I'm gonna check it out.
Pretty
We're gonna
standard.
see.
Stuff.
The penalties for like,
Well, let's see here.
What is it?
Did you get 0 too, Daniel?
Like, over
Did you get 0?
compounding.
Or just the whole thing?
And then there's like
I mean,
also,
that honestly makes sense.
And
We
also,
just
like-
could not be laid already.
there was some like pre-screen like stuff about like keeping the compound.
So we could do
Like,
this.
not allowed to
Yeah.
make like any even minor modifications to the
Actually,
regulations,
it's here.
which I mean, I don't think is. I
Huge.
don't know. It's like,
No, but yeah. Oh.
yeah, maybe we can ask. Solve that. But yeah, like, that, yeah, eventually the next day.
I just like that. That's kind of crap.
Yeah, and then.
Just
no,
a
it was
quick
just, like,
note,
simple stuff.
you could pull the YZ out front here,
That was like
because that integral doesn't depend on the Y and Z, so
Yeah.
they're just
Like,
constant
no
there.
growing, no possession.
And then you've just got an integral of x dx, which is 1/2 x squared. When you work that through, you get 1/2. So the integral from 0 to 1 of x dx is just 1/2. So let's see what we got here. So we got minus 1 to 1,
Specifically, what's this?
integral 0 to 2, so then I've got 1/2 yz. And again, now I can pull the z out in front,
It's just a shame I can't.
but not in front of the whole thing, just in front of that integral. I can pull the 1/2 out in front too. 1/2 in front of all of it, so then we've got dc.
Oh, I see.
So this is 1/2
Oh,
y
right,
squared
okay, yeah.
0 to 2.
Like
That's just 2.
Yeah.
It's not a big thing. I think we could just like throw that on as like, if we could look completely short.
DZ. And then the 2 and the 1/2 cancel. We've just got integral minus 1 to 1 z dz. And that is 1/2 z squared minus 1 to 1. And I believe the answer is 0. Kayla, yes.
So we started with integrating z first and got 0.
Yes.
But so
Oh,
what,
cool.
what's like the integral of 0? Is it just 0?
It's just 0.
Okay.
Oh, that's smart. So you actually did the 0 first? Wow.
Yeah.
Nice. Let's check that out, everybody. That's pretty sweet. Yeah, so if you do, let's see, so we rewrite it. You did something like this. You had the minus 1 to 1 on the inside, and then you had dz on the inside, and then these other guys, it's dx, dy. I guess it doesn't really matter once we get 0, does it? And then see, what's the x range? The x range is 0 to 1, and then the y range is 0 to 2. So let's see, so you did the z integral first. Now notice here this y's x, xy you can pull out in front. So it's just that, from minus 1 to 1, and then integral 0 to 1, integral 0 to 2. Looks like we know something, right? Like this is pretty intense mathematically notation. Math notation looks awesome here. So this is 0. So you're done.
Right.
Yeah, good stuff. Yeah, yeah. So you could have got 0 a lot faster.
Nice.
Yeah, good work. Good work. Let me stop. How's this feeling?
I don't know why.
Not bad, right? Not bad at all.
Just that's why I say not
I don't know what book is
Is this
This one? That is a Z, yes, sir. That's a 2. That's a 2, yes. Ah, now you got it. Yeah, you're having trouble. That's yeah, it's fun to guess people's numbers, isn't it?
This big, like a double
It's like $6. All right, I kind of want to push this into us. I feel like we got this. If we can integrate, right? We can do this. I want to push this somewhere more interesting. So, pretty often you have rectangular areas, but not all the time to integrate over. So what if what gave us this new problem? Find the area, the volume under, and here we're just going to use f of xy equals, just x plus 2y, or x plus y, heck, why not? Find the area under z equals this. Now this is some plane kind of sitting up, angled up in the XYZ space. Find the volume under this above, and I'm going to draw the region here. Here's X, here's Y, and we are going to go from 0 to 1 on the x-axis, but then this is the line y equals x here. So instead of a rectangle, now I've got a triangle. And I can't just do the rectangular area and take half of it, because I don't know what this space is doing up here. Yeah, sorry. It sounds like a nice plan, and it might work out, but it's a total fluke. So what we're going to do is we're going to think about slicing this region up. So the first thing is, I'm gonna almost imagine then that I'm integrating it on its own. So think about how you would set up the integral for this space here. If we made vertical slices of thickness delta x, so down here I got a little slice, delta x, at a given x coordinate. So I'm going to slice this thing up like this, make little slices like this. Notice that the shape of each slice changes, right? They're getting longer as I move this way. So if I'm at a particular x, how high is that slice? So if I was at a quarter, how high is that slice? A quarter. Is that what you were saying, Kayla? You were mouthing something, but I wasn't sure.
I was just saying like y equals x.
Y equals x. Yeah. So exactly, yes, exactly. So however far over you are, that's how high this slice is, because the height is governed by the x coordinate here. So if I moved here, it's going to change. If I move out here, it's going to change. And then that very last slice has 1 as its height. So let's call this t here. And what we're interested in is the double integral. It's double because there's 2 input variables over t of x plus y. And then I'm going to put a little dA here. Now we got to get in here and figure this out. So think about the way I said we're going to cut this up. First off, we're going to do slices from 0 to 1. That's completely determined. Like these slices from 0 to 1, there's nothing variable about that. So I'm going to make that my outside integral. I'm going to slice everything from 0 to 1. Now, for each x slice that I take, what is the y going to run? And it's going to run from 0, so for a particular x, it's going to run from 0 on the y-axis to y equals x on the x-axis, on the y-axis. Does that make sense? So this inside integral is going to run, the base of the little slice starts at 0, and the top ends at x. And that's going to be my y range. So y runs from 0 to x, and then in here I've got x plus y. So notice how I did this. I sliced the x vertically like this, and then the y slices run from 0 to x. This is the extent of the y slices. So to see if you're getting what I'm saying, I'd like you to try to flip the order of integration. And this is going to be a bit of a puzzle until we understand it a little bit better. You might be getting it now. But what if I want to rewrite this as dx dy? So that's still the same integrand, x plus y, but I'm going to write dx dy. So now that line's still y equals x, but we're going to slice the y-axis as the outside slices. So here I'm going to cut from 0 to 1 again on the y. Let me draw a fresh picture over here. 0 to 1, that's y equals x. So we're going to cut this thing up from 0 to 1, and we're going to make little slices that look like this for a particular y coordinate. So an average y slice looks like this. Where does that start? And where does that end? Where does each of those, first let's go for the low-hanging fruit. Where does each horizontal slice end? It ends at 1. So the x coordinate for each y slice ends at 1. Where does it start? Now I'm at a particular y value, How do I figure out where this is? What is that? Y equals x. So that's literally just y. So this goes from y to 1. That is the same area. And this is like kind of one of the harder things to think about. That this integral here is exactly the same as this integral here. And if we did them, we'd get the exact same value. Yes, sir?
Sorry, I'm just.
Yeah.
I missed.
No, it's okay.
Something, like we're going from Y to 1, where's 1?
Do you want me to kind of go through it again real quick?
Yeah.
Okay.
If you could.
Sure.
No,
So,
I'm like almost there.
yeah, no, absolutely. So first off, the y's on the outside. So I'm thinking of slices. I'm slicing up the y-axis from 0
Right,
to 1.
I definitely got that.
Okay.
Yeah.
So now, for a particular y coordinate,
Uh-huh.
where does the x coordinate start for that slice? So notice, the horizontal slices are longer here and shorter as I move up, and they depend on the y slice I'm at.
Right.
So if I told you, Alexander, I'm at this slice and its coordinates y, where would it start on the x-axis? And the answer is it's exactly at that y
Right, because
coordinate.
Y equals X.
Yeah.
Okay.
And then it runs all the way to 1, no matter where the slice is. They all end at
Right,
x
so
equals
that-
1.
That final round is 1?
Yes, yes.
It's not a
This-
corrected 1?
No, no,
Okay.
it's a 1.
Okay, that makes sense.
Does that make
Yeah,
sense?
I didn't.
Yeah, no, this is good.
Some information, so that makes sense.
Let's do one of these, because now we've got a variable limit on our integral. So check out what's going on here. Pick whichever one you like best, but when you plug in the limits here, you're going to be plugging in a y before you integrate the outer one again. So maybe, I'm gonna do this one, maybe we could all do this one and just go slowly together. Because you gotta integrate with respect to x first. And you got to evaluate from x equals y to x equals 1. Please use those labels like that. So that you remember who's getting plugged.
Oh, yeah.
It's all good? I gotta repeat right back. Did I get that right? heard like muttering out there, it's like, shit, I'm not doing this wrong. Wow, that worked out really cool. One? Anybody else get one? No? Maybe I'll double check. Would you?
Shouldn't it just be 1/2?
I got one.
Yes, thank you. Yeah, because, yeah, yes, it should. I got a little excited. Should be 1/2. Anybody else get 1/2? Yeah. Okay. Cool. Well, I think that might be it for today. That sound okay?
Yep.
Because we're coming back to this on Friday, but nothing you have to do for Wednesday has anything to do with this. Just remember. If you have any troubles between now and then with the web work, let me know. If you want to talk about any of the problems, let me know. We can figure it out. That's not too early. That's not too early. I think I owed you guys.
Makes up for
some time
Friday.
anyway. What's that?
Makes up for Friday.
There we go. Yeah, that's right. That's right. I'm all about equity.
Yeah.
You know I do.